Hello, welcome to this supplementary video for Phys 1104 on using a spreadsheet to analyze a motion with non-uniform acceleration. Before I dive in with the spreadsheet, I want to put what we're doing into the context of this picture, because although we're using a spreadsheet, we're actually doing things in this picture. We're going to have a non-uniform acceleration, and so what we want is to use that to find changes in velocity using the area under the acceleration versus time curve. And then we can further go on to use those non-constant velocities that we get and find areas under those graphs to get position changes or displacements. So what we're in fact doing here is integrating, but we're doing what's called a numerical integral using the spreadsheet instead of an analytical integral using pen and paper. So what we're doing is essentially what's shown in this picture. And if you remember from another lecture where I talked about this, if we wanted a displacement from some time to another time, we would find the area under the Vx versus t curve. And if it's a curve, we might not know how to do that, but we can draw rectangles under it. And the more rectangles we use, or in other words, the smaller our time intervals are, the better the approximation gets. In the limit, as the rectangles approach zero width, we get the integral. But we're not going to do that. Using the spreadsheet, we are forced to use finite width rectangles. But if we make them narrow enough, we're going to get a good approximation. But we're not going to start getting a displacement from a Vx versus t curve. We're going to start getting changes in velocity from an Ax versus t curve. But the idea is exactly the same. It's just an area under the Ax versus t. If you know some calculus, you might be wondering why we would bother to do this and not just take the integral using pen and paper, because that's actually easier than using the spreadsheet. Well, there are several reasons. For one thing, at the moment, many of you might not know how to take those integrals. For another reason, sometimes you don't actually know the function. You might know accelerations at various times, but you might not know a nice function that you can draw through them to take an integral of. And still another reason, which I think should be mentioned in calculus courses more often, is that there are functions that cannot be integrated analytically. And with those functions, we have no choice but to do a numerical integral, the way we're going to do here. So now let's dive in with the spreadsheet. I've set up a spreadsheet here where I have a column of times. And I'll just point out that I've set a time interval, delta t, over here, and I've used that to build this column of time. So if I want to change my time interval, I can just do it instantly. That's going to be useful. And I've made up an acceleration versus time function. Don't worry about what the function is. I've graphed it. The point is that I've got a non-uniform acceleration. Now this is the simplest case, where we just know the acceleration as a function of time. But you might be working with some other situation. Maybe, in fact, you're in the lab and you've got acceleration versus time data that you've got using an accelerometer, and you want to use that to infer how far an object has moved. There are practical applications where this is done, such as with your smartphone. Or you might know about the forces, and you could be using the forces to determine the accelerations, and then using those accelerations again to determine the velocities and displacements. So now let's use this idea to get velocities. The way we're going to do it is we're going to use a familiar equation. We have a UAM equation, VF equals VI plus a, I'm going to put some X's on here, delta T. And you might be objecting, wait a second, Jeff, this is a uniformly accelerated motion equation, and this isn't a uniform acceleration. True, But over short time periods, the acceleration doesn't change much, right? Here's a short time period, and the acceleration doesn't change very much. And so I can approximate for, say, the first 0.02 seconds that the acceleration is just this initial value. And so what I'm doing is effectively saying that my delta V will be the area of this rectangle, where the rectangle has the height that's coming from the value of the acceleration here, and the width of this rectangle is my delta t, which is my, at the moment, 0.02 seconds. So let me put that in. I'm going to say that v at t equals 0.2 is my previous v plus my acceleration times tf minus ti, right? That's delta t. And so there is an approximate value for vx at t equals 0.02. Well, now I can do the same thing to get my value of x here. And again, I'm going to use a familiar equation, a UAM equation. xf is xi plus vi x delta t, and so on. And so again, here, I'm going to use the previous velocity and the previous acceleration. I'm again approximating over this short time interval that the acceleration is nearly constant. So let me do that. So my x at 0.02 is my previous x plus the velocity at the beginning of this interval times this time interval plus a half times the acceleration times the time interval squared. And now, because all of this is just referring to things on the previous line, all I have to do is grab this and fill it down, and I now have my velocities and positions at all of these times, approximately. So now I've plotted up x versus t and vx versus t so you can have a look at them. The point I want to finish up with is how well this works, and that in this case at least we can test how well it's working. The function I'm using for the acceleration is the square root of at plus b. That's just, there's nothing special about that. I just made it up. And here are my constants a and b that I used in that. If you know some calculus, then you can integrate that twice and show that x at 1 second should be about 0.8451 and many more digits. Okay, so let's see how we did with our spreadsheet approximating this. If I go down to t equals 1, we see 0.8222. Well, you know, that's not terrible. It's not fabulous, but it's not terrible. But remember, I set this up so I can change my time interval. So I'm going to take smaller, narrower rectangles. Okay, and now if I scroll down to 1 second, I get 0.830397. Okay, so that's closer. And, you know, I can keep going. Let's go down to 0.0025 for my delta t's. Okay, and now I have to scroll down fairly far to find 1 second, but it is 0.83648, right? And so it's definitely getting closer. And this is the point, right? That as we take the limit as our delta t gets smaller and smaller, This approximation, which is just drawing rectangles under our acceleration versus time graph, is going to get closer and closer to the precise result which we would get from the integral.